What's that?
Was that not Zach, or did he leave? Or was that like Will?
It was me.
Oh, nice. I legit thought that was Zach.
Yeah, but you can't tell me it would be funnier if he walked in, said "was up," and just left for the day.
It sounds like something he would do.
What's that? What's that? What's that? Nobody else?
Me?
Yes.
I don't know. I don't have it in with the dentist. I want to spread cavities.
Oh, I thought you'd have a buck of candy since you drive a white van.
Work something out with ice cream, maybe, but not candy.
Oh boy. All right. Anybody have any trouble with that? Wait a minute. Did anybody get arrested this weekend?
Wait, our
eBay?
teacher got arrested?
Well, I always get arrested. That's why I always raise my hand. But I can't talk to you about it. Still under investigation. eBay, you look kind of guilty. What'd you
do? No, I didn't do anything. Just
Yeah.
I raced.
Okay.
Take race.
Okay. All right. Well, how about the homework? What chapter are we on? 5?
Oh, was that
Yeah.
due today?
It was.
Wah, wah.
I forgot all about it.
I see that.
I'll be honest, I just did mine about 10 minutes ago.
We did pretty darn good for doing it 10 minutes ago.
I know, it worked out good.
Good grief.
I finished it with like 2 minutes left. I could not believe it.
Okay. Let me jot down who's here real quick so we can go over the homework. Everybody have a good weekend?
I had a fish fry at my parents'
How
house.
about you?
Fish fry is good. Fish fry is good. Anybody else? Ethan went to a wedding. Ethan got married on Saturday to his cousin,
Yeah, that's true.
James is his name.
Wait, he's from Alabama?
No, Princeville.
Gotcha.
They do that out there. Get off his ass. Let him live his life, dude. I'm just kidding. Ethan, you can defend yourself against me and my smart assedness.
No, you're right. I just didn't tell you the truth.
I caught Ethan on the way in, and first my dumb ass is like, "Hey, what classes do you have today?" He's like, yours?" Like, oh, duh. Then he said he went to a wedding, and I always liked weddings though, at least the first parts. And then when everybody gets all drunk and stupid, I'm like, eh. Did you dance?
I did not dance.
Oh, that's my favorite part. Get out there and do the stanky leg. Get it. No? Okay. You guys want me to just shut up and get this done so you can go back to bed?
How can I go back if I never left?
Good point. Good point. Maybe you should have gotten out of bed and done your homework.
Yeah, I forgot about it.
Maybe I'm just saying.
I've been awake. Took care of my brother.
I do respect that. Taking
Mm.
care of kids is not easy.
No,
How old is he?
like 2.5.
It's a fun age.
Yep.
Here we go. A DC motor, blah, 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 blah. Which one are we choosing here?
It shouldn't be operated without a load.
Truth. Should not operate a DC motor without load. Really shouldn't. Well, never mind. Question 2, I had that as extra credit for some reason. A blank is an example of constant horsepower load.
Lathe.
A lathe. Why did I make that extra credit? A conveyor? Why wouldn't that be constant horsepower?
Because you need to stop and slow it down.
Yeah, I suppose so. And it could become, as things get placed on and taken off of the conveyor, that the horsepower output of the motor would be different.
Hey, there's a murderer behind you.
No, that's just McKinn. Why wouldn't a fan be an example of a constant horsepower load? I don't know. In my mind, I kind of think it would be.
I thought it was. Is it
Not
not?
here. I don't know. And I don't know what the book said specifically, but
There was a good passage explaining, but I don't remember what it said to explain it to y'all really.
I suppose a fan would be turned on and off. But so would a lathe. I don't really know. I guess that's why I made it extra.
Does the lathe just go at one speed?
Well, yeah, you're only at one speed, but you think about it. Do you know what a lathe is?
It can change speeds going faster too.
Yeah, and as you ever seen you know what a lathe is?
Yes.
Anybody not know what a lathe is? I mean, this is a lathe. So a lathe spins the part spins, right?
In straight turn, the tool is fed parallel and be turned
So-
using
so-
a compound
yeah.
press. Based by
So this is a lathe, and then you take, look, they're making a ball hitch. That's cool.
programmed into the machine, which directs a cutting tool. to
So it
cut
takes
the
off a little bit of material at a time, but
Forming is another.
so everybody knows what a lathe is. If you think about it, if you have a different tool or if you're taking off more material in a certain area, the horsepower would be a little bit different. You know, the load becomes a little bit different. So, and then a pump. I don't know. I just think it's a dumb question. I probably should have removed it, but I suppose that's why I made it extra credit. Anyway, a motor with a speed of 1800 RPM and a drive pulley that is 2 inches in diameter is coupled via a belt drive to load pulley that is 4 inches in diameter. What is the speed of the driven load?
900 RPM.
900 RPM. Do you need me to explain that? No? You guys will do more, not in this class, but in future class, Electech 220. Doesn't matter what program you're in, you will take that class because it's actually part of your, unless you're a certificate. It's our transducers class. And it also doubles as the lab science for your gen eds. But anyway, that class you will do more calculations of like, you know, a pulley and how big it is and what's the load and horsepower. But do you understand that? Do you want me to explain it a little more? Or are you good?
Can you explain it a little more?
Okay. Okay, so 1800 RPM, what does our RPM stand for?
Rotations per minute.
Revolutions per minute.
Revolution.
A drive pulley that is 2 inches in diameter and is coupled via a belt drive to a load pulley that is 4 inches in diameter. The speed of the driven load would be.
Don't you get it from dividing 4 inches by 2 inches? Then you
Yes.
multiply that by the total.
Yes, but if you think of it this way, so this is the pulley of the motor. And its diameter is 2 inches. And the load has a pulley. Oh my gosh. Oh my gosh. That is 4 inches in diameter. So here's your motor, and then you've got a belt doing this kind of thing. So if the speed of this one is 1800 revolutions per minute, and it's asking what would the speed of this one be? If this is 2 inches in diameter, one revolution, how many, I guess, how much of the belt is actually moving past one point in time? So at this point in time, at this point in 1 minute, how much of the belt is going past it? So let's say we're spinning this way.
2 pi inches.
Right. So we have to find the circumference of this, right? The circumference of that would be pi times diameter, so 2 times pi. Just 6.28. So in 1 minute, there's 6.28 inches in a revolution, right? But this thing spins one time around, it's traveling, the belt is traveling 6.28 inches. So 6.28 times 1800. I'm probably doing way more math here than I need to, but why not just keep going with it? What is 6.28 times 1800?
Is that 12,276?
What'd you say it was? 12,276 inches per minute. What about this one? I think I'm doing way more math than I need to.
You are.
So this would be 4 times pi for the circumference, or were you asking for the RPM?
I think I'm doing way more math than I need to.
The book it just sets them up as 2 fractions that are equal to each other.
Yeah, well, forget all this crap. This is something for a different class later on down the road. I guess the simple answer would be, if this thing spins once and it's turning this, is it rotating at the same speed, or is it rotating the same amount? Because the smaller pulley is driving the bigger pulley, right?
Yeah.
If this is 2 inches in diameter and this is 4 inches in diameter, as this thing spins one time, how many times does this spin?
Less than 1.
A half.
Yeah.
Because if this is 2 inches in diameter and this is 4 inches in diameter, then this circumference should be half of that, right? So in one revolution, this spins a half a revolution. So if this is at 1800 RPM, this would be at 900 RPM, right? If it was 1-to-1, if this was 2 inches and this was 2 inches, this would be 1800 RPMs. What if this was a 2-inch pulley and this was a 1-inch pulley?
It'd be double.
Right. As this guy spins once, this smaller one would spin twice, right? I think I just did a horrible job of explaining that to you, but do you understand it or no?
Yeah, I did.
Okay. Keep that math in mind for later class down the road, because we will get into that. All right, what are we doing here? Permanent capacitor motor does not require centrifugal switch, uses identical run and auxiliary windings, provides improvement of a power motor factor, or all of the above.
All of the above.
Squirrel cage rotor consists of which one of those?
Single bars short-circuited by end rings.
Yep, and that's how it gets its name. This looks like, kind of looks like a squirrel cage or a hamster wheel. Variable AC motor drive delivers what to the motor?
Variable voltage and frequency.
Correct. You guys will learn more about drives later in this class. A variable AC motor drive is able to operate the motor at base speed, above base speed, below base speed,
All of them.
All of them. Kind of cool, right? I talked to you guys about frequency a little bit, right?
I'm pretty sure. Yeah.
A voltmeter check of a motor should show voltage within what percent of the motor's nameplate voltage?
10%.
10%. An electric motor uses blank energy and blank energy to produce mechanical energy.
Electric and magnetic.
Electric and magnetic. Kinetic and nuclear. Wouldn't that be fun if we had nuclear powered motors back there for you guys to work with?
Sounds like lots of fun.
Mm-hmm.
Look some shit up.
Some shit up. Direct coupling of the motor shaft to the driven load results in what speed ratio?
1-to-1.
Yep. NEC 430-.22 requires branch circuit conductors supplying a single motor to have an ampacity not less than blank of the motor full load current,
125.
125%. Which NEC article is the main code source for electric motor installations?
430.
On a three-phase motor, the stator windings are arranged to create
A rotating.
Yay! You guys remember that from my motor lecture like a month ago. One advantage DC type motors have over AC types is what?
Their speed can be easily varied.
Easily varied speed. How would you adjust the speed of a DC motor? Just increase or decrease the voltage. That's it. What kind of motor is the highest starting torque of all single phase motor?
Capacitor start, capacitor run.
Two basic categories of motors.
AC and DC.
The direction of rotation of a three-phase induction motor is determined by
Phase sequence.
understand that? How do you reverse the rotation of a three-phase motor?
You just switch two of the wires,
Two of the leads.
two leads.
So if this is line 1, line 2, and line 3 coming into the motor to A, B, and C, and we're going like this, A, B, C, right? Rotating magnetic field. What if we switch A and B? Or what if we switch B and C? Then it's going A, B, C, counterclockwise. So that is called phase sequence. And on your forward reverse motor starters, if we want to reverse the rotation, do we have to do anything? Nope.
Just energize the other coil, right?
Yep, it's built right into these things. I think I showed you this, but I'll show you again. This is your motor starter, right? Can you see me?
Yes.
Okay, because I can change cameras, but remember these guys here, you're only landing on one side, these three. But if you look up at the top, these little insulated buses, that's what does the rotation. So if you look closely on here, it goes 3 to 1, 2 to 2, and then 1, 2, 3 over here. So it's switching A phase and C phase. Direction of a rotation on a split phase motor can be reversed by interchanging the connections in which one?
Either A or B.
Yeah, but that's not A. Which one's A and which one's B?
Uh,
That one was confusing.
It's either the start winding
just-
or the run winding. That's
Yeah.
dumb. So it looks like the order of those are just out of whack. But just remember that if you happen to see that on the quiz, it's either the start winding or the run winding. What's the purpose of a commutator in a DC motor?
Maintain the proper direction of current flow in the armature conductors.
Well, which of the options does a series type DC motor have?
High starting torque.
Shunt type DC motor is known to have what?
I think it was good speed regulation.
Yep. A lot of this stuff, like the ways different type of motors and how they're built and whether they have low end torque or high end torque. A lot of that you guys will never need unless you're in the business of designing something. Morning, DeRay. Unless you're in the
didn't
business.
wake up.
What?
I've been awake. I'm just tired.
Okay. I don't even remember what I'm saying, so we'll just move on. Synchronous speed of a 2-pole 60 hertz AC motor.
$3,600 RPM.
Yeah. How would you define torque?
Turning force of a motor.
Yep, it's a rotational force. When a dual voltage 9-lead Y-connected 3-phase motor is connected for high voltage, the individual coils of each phase are connected in. You should all know this one.
Series.
Series. What kind of torque is the torque produced by a motor functioning at rated speed and horsepower?
Full load.
Full load. Any questions on that?
Number 25, I said it's full load, but I got X. I didn't got the point.
What? What?
Question number 25?
3?
25.
Oh,
Last
20,
question.
25.
Yeah.
Yeah.
I said full load, but I got X. I didn't get the point.
Full load is wrong?
Yeah.
Let me check.
Okay.
You didn't select full load. You selected locked rotor.
The other question, question number 11.
11?
Yeah. Where
Yeah.
is the, I can't find the, that question on the book, on the tickets book.
Did anybody else find it in the book?
Yeah, it was so it wasn't in like a paragraph, it was like kind of a separate like math problem in like a blue square kind of around where I forget what the section is. It was like the second to last section of the chapter. But it's on like the top right of it. I'll try to find it.
You guys don't have code books, but you should have one of these, right?
It's page 143, is the torque information.
It's also I have it on 149. There's example 5.6 on 149 on the top right, and that also has like the same information.
Yeah, I see it. Thank you, guys.
You got it? Anybody looked at your motor stuff and in your uglies book? Of course you haven't. Why would you?
What
There's
page?
a lot of good stuff in here, though. Full load current of three-phase AC motors, full load current, another blah, 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 blah. But if you look at the subscripts of all these tables and stuff that's in your uglies book, source NFPA 70E table 430 dot blah, blah, blah. 430 dot this, 430 dot that. Anyway. Ooh. Three-phase AC motor windings and connections. Didn't I tell you you could use uglies books on your quizzes and stuff?
Ooh.
Ooh.
Bless you.
God bless you.
Goodness.
Bless.
God bless.
Thank you. All right. Any other questions to do with homework? Onward and upward. How did Friday go?
Went pretty well.
Did you guys get through all the labs that you wanted to?
Yeah, I got
Almost.
9 and 10. Just need to do 11.
Sweet.
I still need to do lab 11 or the last lab.
Okay. The next one, I believe, is proximity switches. Oh my gosh, are you serious? Oh, timers, that's right. Okay. Um, be right back. Take a break. You're just too good to be true. Can't take my eyes off of you. You had the reason to touch. I just want to touch your butt. Say that out loud.
I didn't hear anything. You
I
should say
heard
it
you
again just
sing
to make
Ba
sure.
Ba Black Sheep.
Oh boy. Oh my goodness. All right, good enough. Hmm. Here we go. Do you think all the other teachers out there in the world are as sophisticated as me using Microsoft Paint in lectures?
They're not as cool as you, at least.
Brownie points.
I used to have a teacher that didn't know how to use a computer.
Really?
Oh yes, he did everything by paper and by hand.
You're just too good to be true. Can't take my eyes off of you. So much. Bloop. Timers. Okay, I'm ready. Thing about timers to remember is this can get a little confusing, but there's on delay and off delay timers. Okay. On delay means that when its coil gets energized, the contacts won't change state until after the given amount of time. So let's just pick a standard time, and all timers, most timers are adjustable, right? But I'm just going to say 3 seconds. So let's say any timer that we're looking at here, we've adjusted the setting for 3 seconds, okay? Just keep that in mind. Let's focus on this first. If I have a symbol of something that looks like that, is that normally open or normally closed? Actually, that's a bad example to start with. Is that normally open or normally closed?
Normally open.
Normally open. And then if I drew this, what is that? Is that normally closed?
Yes.
Actually, with limit switches and timers, the action of these are up, right? So if you see a drawing like this, this is normally open and it's in its de-energized state. On any print you ever see, if you see a symbol for something, it should be shown in its de-energized or relaxed position. So this one is actually normally open, held closed. Tricky, huh?
You got me.
I got him. If that's the case, what is this? Looks pretty similar to this one, doesn't it? Those are pretty similar, right?
That one be normally closed. Since it's on
This
top.
is normally closed because the toggle or whatever you want to call it is sitting on top of that contact, right? So what would this be?
Normally closed, held open.
Normally closed, held open. All right. Normally open, normally closed. So these two are the ones you really need to concentrate on because those are in the de-energized relaxed position. If you ever saw these ones on the right on a print, it should say on there something. You shouldn't have to decipher that, why would there be a held closed switched on a print? Okay. Anyway, keep all that in mind. So this is normally open, this is normally closed. I'm going to delete all this stuff And then we're gonna do for a timer. If this was a limit switch, it would look like this, right? It's just a normally open limit switch, like this one. But on a timer, they have these little things called these things. I don't know what they're called. But this is the symbol for what kind of, is this normally open or normally closed?
Normally open.
Normally open, and since the arrow on the timer part is pointing up, it's an on delay. So this is a normally open on delay timer. So let's look at what a normally open on delay timer does. In this example, forget the 3-second thing. Let's look at TR1 because that's a normally open on delay timer. Okay. When the coil of TR1, well, where is the coil of TR1? What rung?
Seven.
7. Right here. This is the coil for TR1. When that gets energized, what happens? This is an on delay timer. You see how the two sets of contacts associated with that timer are both in the on delay state? So the timer itself is actually an on delay timer. So an on delay timer, 10 seconds later, those will change state. On delay means that when the coil is energized, the delay happens in the contact's action, all right? So when this gets energized, 10 seconds later, TR1 contact normally open will close. And a normally closed on delay timer looks like this. Shit. Why did I do that? I'm thinking ahead, I'm sorry. So this is a normally closed on delay timer. So TR1's coil gets energized. 10 seconds later, they change state. So on this print, and what you guys are actually going to wire up in the lab, when I close LS1, what's going to happen?
Coil will be energized, and
Red.
the time delay.
Right. So when the coil for TR1 gets energized, 10 seconds later, these two will change state. So 10 seconds later, the motor will turn on and the light will turn off. So that's on delay. What if, shit, did too much Control Z in. What if I did this though? What if I made that like this? So now you have a normally open off delay timer. Or let me rephrase. This is an off delay timer coil now. And you have a normally open and normally closed. So what happens there?
As soon as you energize it, would they change and then default back after the
Correct.
time?
Correct. So the off part of off delay timer means the coil's changing state happens when you turn that coil off, when you de-energize the coil. Okay. So what happens when you energize TR1? So I close this. TR1's coil changes state. So this closes and this opens. And then 10 seconds after you de-energize the coil, that's when it changes state. So let me back up. If I close this switch right now, what happens? Coil energizes, this closes, and this opens up. So as soon as I energize the coil of TR1, the motor turns on, and the red light turns off. The delay happens when I open this back up. So I'm going to open the limit switch back up. And 10 seconds later, this will open and that will turn back on. Make sense? It gets kind of confusing, but you have to kind of run through it with your head. When you see these things on a print, you have to look at this and say, okay, this is a normally open on delay timer, which means when the coil energizes, the motor starter won't turn on until 10 seconds later. The on delay is associated with the coil. And this is a normally closed on delay timer, which means that the red light's going to be on, and this is not going to change state until 10 seconds later. So I'm going to do an example for you now. Let me real quickly show you. Some of you have these. Your control relays look like this because this thing is tacked onto there. All that is this timer is bolted to the front of your relay. So these timers, these NEMA timers work in correlation with this coil. Okay, so this is the same coil changing the states of these contacts as this. All this is a set of contacts with a timing plunger inside. I'm going to open this up and show you how it works. But on this timer, I have a normally closed and a normally open set of contacts. So these two are normally open and these two are normally closed. On the back side, this little spring-loaded tab is what sits onto this red indicator. When this coil energizes, remember this thing gets sucked in. So that changes the state of what's going on with these contacts. And I want to show you, like, can you hear? Let me bring the microphone over here. So this is sitting there on that red indicator, all right? And I'm going to let go of it and see if you can hear something like a click, maybe like a half a second after I let go. Ready? Let go, and then a click. This is an on delay timer. Which means that when the coil gets energized, a certain amount of seconds later, it changes state of the contacts. So I'm going to adjust. By the way, this is the dial. See how it says plus and minus, and there's a little picture of a clock. I'm going to adjust the time to make it a little bit more obvious. And when I do that, you see the little plunger inside there going down. And here's the amount of seconds roughly that you're working with. So I'm going to adjust it a little bit. I'm gonna let go of that plunger in 3, 2, 1. Let go. And then you hear the click. Did you hear that?
Yeah.
Can you hear that? Okay, good. So I'm gonna do it again. Ready? I'm gonna let go now. It's still about a second. I'm gonna adjust it for even longer. Try to get it a few seconds. All right, got the plunger up. I'm gonna let go. 2, 3. Oh, that was about 3 seconds. Did you hear the click? Let go. 1, 2, 3. There it is. Make it even longer. Let go. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. About 11 seconds. Kind of cool, right? So now I'm going to take this thing apart and show you how it works on the inside. Shall we?
Yeah.
And by the way, you guys are welcome to take these apart in the lab and investigate them yourselves. This is how I understand things the best too, is by taking it apart. The contacts themselves work a lot like these do. Remember I took this thing apart and you can change them from normally open to normally closed just by flipping them around. Same thing goes here. And I could take these apart, but I've already done that to show you, like you can actually take this, flip it around and make it a normally closed, right? So this one's normally closed and this one's normally open. I want to take the timer guts off of there to show you how that actually works though. So inside of here, you've got a little spring-loaded do that on the back and these little mechanisms down inside there are actually what changes state after this part runs its course. So when I push down on that back part, you see those little mechanisms moving. Those don't happen until the middle part of this little bladder runs out of time and trips it. And then it changes state. You see that? So here's me pushing down on the backside of the plunger, and then the timer will run out and oh, can't get it to do it. Change the state of the contacts. Okay. The timing part itself is actually this little bladder, really sophisticated, but it's cool. And I love these old timers. This little bladder holds air. Depending how you adjust this screw, you will see this thing come out quickly. What was it, 11 seconds? 1, 2, 3, 4. You see that little gap getting smaller? 5, 6, 7, 8, 9, 10, 11, until eventually it gets all the way back out. If I adjust that down, then you'll see that plunger pop back out pretty quickly. Ready? 1, 2, 3, 4, 5, 6, 7. Can you see that though? Can you see the difference in speed?
Yeah.
Let me adjust it way down so it comes back out really quick. Ready? Pretty quick, right? See how it comes out really quick? And then if I adjust it way up, it takes a long time for it to come all the way out. Follow? So that's what's happening on the inside there as you adjust that timer. And remember how it actually trips is this white part will come down and hit this middle mechanism, changing the state back to what it's supposed to be. So that is how the timer works for a NEMA. Last thing, ready for this? Remember how it was on delay before? Remember I showed you that? I would release the plunger on the backside, and then a certain amount of seconds later, it would change state. What if we wanted to make it an off delay? Oh, cool. We flip this thing upside down. Now do you see up at the top, it says delay off. So we just changed it from an on delay to an off delay timer. I'm gonna put this thing back on there. So what happens with an off delay timer? When you energize the coil, when you energize, I would not put that back together. Something is amiss. Anyway, I think I broke something in there maybe. By switching it to off delay, now when we energize the coil, as soon as that coil pulls in, these change state immediately. And then when you de-energize it, that's the amount of seconds that after you de-energize the coils when those contacts change state. Understand the difference between on delay and off delay? And with these, it's really cool because you can change it from an off delay to an on delay just by doing that. Cool.
Cool.
All right.
Okay.
IEC. Somebody have a question?
Yes. Would those snap on? Would those be considered as auxiliary contact? Or?
These? This?
Yeah.
No, they're not auxiliary because they change state according to the time. You know what I mean? They actually do make, and I can grab one. The same way this works by sitting on that red indicator, right? So this is all working according to this coil being energized, right? This is the same as it always was when you guys use this. As soon as this coil energizes, all 4 of these change state, right? That's a control relay or a contactor, however you want to say it. The coil up here energizes and this thing pulls in and all 4 of those change state immediately at the same time. When you slap a timer on there, it works off that same coil, but these change state according to the time. It's either on delay or off delay by switching this around, right? So it's not auxiliary contact, but they do make an extra set of contacts, and I can get some and show you if you want me to, but it slaps on there just like the timer does, but it's just another set of contacts, right? So if you had, let's say I want to control more than 4 circuits with this one coil, I could slap another one of those on there and control them with that same coil. So this is the IEC control relay, right? Look familiar? Should all have that on your trainer. 120 volt coil, when this energizes, all 4 of these change state. This one happens to have normally open on the outside and normally closed on the inside. So normally open and closed. Timer works the same way. And these are nice because they're DIN rail mount. These things just kind of slide into place. And some of you, I've taken these off for you so it's easier to use the back side, but this is actually what's going on here. And it all works the same principles. The guts are pretty much the same. This is the dial to adjust the amount of time on here. And you've got a normally open and a normally closed. This one is an on delay, and it says right there, you can see that. It says on delay right here, 0.3 to 30 seconds by adjusting this dial, which means that when the coil energizes, and I can't simulate on this one because, I can by taking this off, I guess. Right, so this part here is sitting on this is, I guess, the same as that red indicator, right? So when the coil energizes here and pulls in, that means this thing changes state. Now it's an on delay, so I'm not hearing it click though. Let me adjust it. Right, so I'll let go of the plunger. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I guess this one doesn't have the clicking action in it, so you can hear. Oop, did I just hear it? This one, you can tell by the way that this is all gnarled up that it's been used a lot and it's not turning very easily. So I wonder if this one's kaput. But these things, like while they're handy, they're light, they're easy to mount. Remember I told you this guy, you can change on delay versus off delay. You can change the contacts to make them normally open or normally closed. This one is, when you get it, it's exactly what it is. You can't change it. So if you wanted an off delay timer, you would have to buy a new whole entire one of these. And if you wanted that off delay to have both normally open, you would have to buy it that way, right? You can't make those adjustments like you can with this. So NEMA IEC. All right, now I want to do a quick example with my trainer, but I don't want to use, I guess I could use this example, but this is not going to be like your lab. It's going to be a little different. I'm going to make let's see, TR1. Okay, I'll use it as an on delay. So I got a normally open, normally closed on delay timer, but I'm going to make this one a light just to make it a little more simpler. So this is the green light and a red light. Okay, and obviously I don't have this crap here. So all I'm doing is this portion down towards the bottom. You can imagine this coming straight off the transformer. Whoops, whoops, whoops. All right, so I need a 1 going to each one of these, and then I'm going to call these 2s, which makes this 3, 4, and 5. I'm going to do my wire number 1s first. Remember, this is going to be a little different than your lab, but all this other stuff up here, you should know how to do all of this by now. So I'll show you. This is your lab, right? This is what you're going to do for lab 12. What I'm focusing on is this area down here. This is the timer part, all right? So in your lab, it's going to be, you got 2 push buttons. Either one of them can energize control relay 1, which you're going to use the ice cube relay. When that control is turned on, green light will turn on. So nothing down here can happen until you energize this control relay. Then down here, you've got a separate stop start. Control relay 2 will turn the yellow light on. And at that point, the limit switch will start the timing process. So once you've got both control relays turned on and you close that limit switch, what's going to happen? On delay. So that means you energize this coil. 10 seconds later, this will close and that will open up. Anyway, back to the drawing board. Okay. I'm gonna take all this stuff off. I don't need.
Ba ba, black sheep, have you any wool? No, sir, no, sir, 3 bags full. One for my master, one for my dame, one for the little boy that lives down the lane. Ba ba, black sheep, have you any wool? No, sir, no, sir, 3 bags full.
That was lovely. Thank you for that. All right, so I need a wire number 1 going to normally open limit switch. I'm just reusing this one. This is actually, I'm just connecting it right here. I also need a wire number 1 at TR1 normally open and TR1 normally closed. I don't have a timer hooked up here. I need to get some screws, put it onto here. So I will be right back. Don't you go anywhere. You go ahead and sing, Will.
Ba ba, black sheep, have you any wool? No, sir, no, sir, 3 bags full. One for my master, one for my dame, one for the little boy living down the lane. Ba ba, black sheep, have you any wool? No, sir, no, sir, 3 bags full. Twinkle, twinkle, little star, how I wonder what you are. Up above the world so high, like a diamond in the sky. When the blazing sun is gone, when he's nothing shines upon, then you show your little light. Twinkle, twinkle all the night. Then the travelers in the dark thank you for your tiny spark. He could not see when way to go. If you did not twinkle so. In the dark blue sky you keep, and often through my curtains peep. For you never shut your eye till the sun is in the sky, as bright as a tiny spark, lights and travels in the dark. Though I know not why you are, twinkle, twinkle, little star.
Thank you.
Twinkle, twinkle, little
Wait.
star.
Wait. Thank you, Will. I'm just gonna pause you for a second. I need a wire number 1 to my timer. This is non-delay. Normally open is on the left. Normally closed is on the right. That's just how this one happens to be set up. Yours might be different. But normally opens on the left, normally closes on the right. So if I need a number 1 to one normally open and normally closed to the other, really all I have to do is take a normally open to here and put a little jumper inside of there, right? Right? Okay, that's what I'll do. Will, please tell me that you have those memorized and you didn't have to look it up.
Which one? Baba Black Sheep or Twinkle Twinkle Little Star?
All of it.
The Twinkle Twinkle Little Star, I didn't know. I just thought it was like 8 lines. Turns out there's more. I
Did you
just
look it
found that
up or
out now.
did you memorize it? Did you look it up or did you memorize it?
I looked it up.
Oh, disheartening.
Well, do you remember what Twinkle Twinkle Little Star?
Yeah, I knew all those words.
Okay, sing Twinkle Twinkle Little Star.
No. All right, so I got a 1 going to one side of the normally open, and I got a 1 going to one side of the normally closed. All right, wire number 3, I need to go from the other side of the limit switch down to the coil of my timer, which is right here, and we're using the same coil that we did with the control relay. It's all the same coil doing the same stuff. Oh, you. so wire number 3 is done. I don't have a 2 coming off of my coil going to the neutral bar. So I'm just gonna steal this one real quick and run it over there. Beep. So this is done. Wire number 4, I need to go from one side of the normally open to my green light. So on my timer, the left is normally open. That would be wire number 4. Wire number 5, I need to go from the normally closed up to the red light. All right, so wire number 5 is done. Now what about the neutrals for my lights?
Those should be hooked up already.
They're done. Remember, we keep running into this with you guys, but the neutrals for all 3 of these lights are all shared on this one wire. It's already made up. It should be made up on your trainer too, unless for some reason you've taken it out. Now that that's done, I don't know what the timing is of this, and I can listen for it on these NEMA ones to hear the click. It's supposed to be about 10 seconds. 1, oh, 1, 2. That was about 3 seconds. Did you hear it? 1001. Oh, 1 second. 1001, 1002, 1003. About 3 seconds. Okay, I'm not going to do 10 seconds to save time. I'm going to leave it at 3. But what should happen when I turn it on? Red light's on because it's on a normally closed contact, right? So when I hit that limit switch, what should happen? An on delay timer.
after 3 seconds, the red light will turn off and the green light will turn on.
Right. The action of the contacts is not going to change state until the timing is done. That's an on delay timer. So here we go. When I close this limit switch, 3 seconds later, that should turn off and that should turn on. 1001, 1002, 1003. Cool, right? I can adjust the time by doing this on this little dial. 1001, 1002, 1003, 1004, 1005, 1006, 8, 1009, 10. Oh, there's my 10-second lab. Cool, I'm done. 1001, 1002, 1003, blah, 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 blah. You guys get the idea. What if I changed it then to an off delay timer though? What if I switched this thing around? Then what would happen? All right, so I just changed that from an on delay to an off delay timer. So now these look like this. Now what happens when I close that limit switch? Think of it this way. The off happens, the delay off, that happens associated with the coil. So now what happens is when I energize the coil, they'll change state right away. And then when I de-energize the coil, 10 seconds later, they'll change state. It's an off delay. All right, here we go. Hi, Mom. All right. So now what happens when I close this limit switch is it should change state right away, and it does. And then, are you laughing, Daddy?
Yeah.
That was my mom.
Oh, okay.
Okay, so it's an off delay. All I did was switch this thing backwards, right? Remember I showed you that earlier? All I did was flip it around. Now when I turn it off, 10 seconds later, it should change state. Or however many seconds that was. You see the difference? Change state right away, let go. Now it changes state. You see the difference between on delay and off delay?
Yes.
That seems to be the most confusing part for students, is recognizing that normally closed on delay versus normally open off delay. Just remember, if it's on delay or off delay, that has to do with the timer itself and the coil and what happens. Okay. Think you got enough information to do lab 12 now?
Yes.
Okie dokie.
Yep.
Yes, sir.
Okay, so it looks like then Wednesday we'll do quiz over 4 and 5 homework. And then we'll cut you loose into the lab to work on whatever you need to work on. Sound good?
Yep.
Everybody happy?
Oh yeah.
More or
Let's
less.
see some smiling faces. 1, 2, 3. Eve, there. Eve. Yep. Yep. Gavin. Yep. Okay. All right. There's Will. Yep. All right. Now, Will, I need you to sing us out of this meeting, unless anybody has any questions.
I had something I wanted to tell you. I got a job offer to work third shift, and I don't know
Yeah.
when I have to make. I'm on normal sleep at night hours right now, so I just wanted to let you know I might sleep through a class or something. Not mean to, but
What's more important, work or this class?
this class.
Work.
Me.
Are you kidding? You have to go to work.
I'm not gonna miss work by going to this class. I might accidentally sleep through this class as I'm making a shift though.
I know what I mean to you in your life. I get it. No, I appreciate you telling me that. And I know you'll do your best to make it to class and just make sure you stay on top of your labs and the homework and the quizzes. So thank you for telling me that. And if you should happen to miss, just get with me and we'll figure it out.
Yeah, I'll let you know.
All right. Anybody else?
Yeah, I got one question. When do like summer classes start?
June.
So they
Right.
just
June.
start right away.
Yeah.
All right.
Well, there's a little gap between your finals and the start of summer, and
Okay.
depending on which class you take. Anybody else?
I like electrical cabinet, industrial setting. Would it have like those rails on the trainers? Would it have like something like that to hold the wiring in?
These,
Yeah.
the C channel, just depending on the, I don't know, the application, the manufacturer, probably. I would sure hope so. Have you seen one that doesn't?
Oh, I haven't seen in any. I'm just curious how that works.
Yeah. Yeah, they should. I mean, because imagine what all this would look like without that.
Hmm.
You know, it'd just be a big bird's nest of wire.
Sure.
Zip ties come in really handy.
What comes?
Zip ties.
Yep, tie wraps, sticky
Oh.
backs. You got sticky backs, Carter?
I've used them before.
Oh yeah.
They're nice.
Yep. Any other questions? All right. Have a lovely rest of your Monday. Will, go ahead and sing us out. Let's do second verse of Twinkle Twinkle Little Star.
1 sec, I have to look it up.
Okay. Daddy, I can see your pussy. Yep.
I got 2.
Oh boy,
So if you don't like that one, I got another one.
you're a lucky man.
Twinkle, twinkle, little star, how I wonder what you are. Up above the world so high, like a